In this module, I'm going to introduce the notion of sequences and summations. One way to think about this module is to view it as application of functions that we saw earlier. Another way to look at it is just a sequence of numbers, and a sequence of numbers where we want to add the numbers in the sequence, and that's what we'll call summations. This is the outline of this module. In this module, I will define sequences. We will look at some special integer sequences. In the next module, I will use these sequences to define the notion of recurrence relation. In the subsequent module, I'll define summations and its applications. And in the next module, I will introduce cardinality, countable sets, uncountable sets, etc. The reason I'm putting this outline over here is because even though I'm splitting this in multiple modules, these are related to each other, and so you may need to go back and forth between these modules as you're studying this. So let's look at what a sequence is. So this is you might consider a complicated definition of a sequence, but it's also to show you how we can use the notion of functions that we talked about earlier to define different things. So what is a sequence? A sequence, that as we understand, is there is something as the first number, then the second, then third, then fourth, and so on. So we can define a sequence as a function from some subset of n is the set of natural numbers, to the set S. So essentially, I could think of this as I have some subset of S, so maybe I have subset 1, 2, 3, 4, and here I have the set S that contains S1, S2, S3, S4. And I'm going to have a function that I'm going to map from this subset of n to the set S. So maybe I have something like this, something like this, something like this, something like this. And that will give me the sequence. First is S1, then I have S3, then I have S2, and then again I have the term S2. So we can view a sequence as a function that maps some subset of integers to a set S. The reason we are calling it from subset of natural numbers is because maybe we want to just define a finite sequence, in which case we won't be mapping every integer to an element in S, but only a few of the integers. We use this notation. The term an is the nth term in the sequence. So if I think of it as mapping, then essentially I have this number n here. It's going to map to something over here, and that term is going to be an. We denote the whole sequence using this notation, where we have curly braces. Inside that we write an, and then we close the brace. Note that in this case n is really in some sense a dummy variable. It doesn't really relate to anything, because you will instantiate the value of n to find a particular element in the sequence. Once again, this notation looks very similar to the set notation, but this is not related to that. It's sort of, you could call a misuse or overuse of notations. So let's look at an example. Here I have a sequence an, where the nth sequence is defined as 1 over n. And so that means the first element in this sequence a1 is 1, a2 is half, a3 is one third, and so on and so forth. So I could think of this as a function where 1 is mapping to half, 2 is mapping to one third, and so on and so forth. Let's look at this sequence. This is a special kind of sequence for mathematics known as Catalan numbers, and it is defined as the nth Catalan number, where n is greater than or equal to 1, is 2n factorial divided by n factorial times n plus 1 factorial. One of the things I would ask you to do when you're reviewing these slides is to find a few terms in the sequence, and I I would I would look at this in class subsequently. The purpose of asking you to calculate this is in part to refresh what factorial is if you've forgotten it, and also to play with sequences and to understand how we compute different elements in the sequence given the value of n. Here is another sequence. It is has some weird formula, uh, but what I'm going to ask you to do is find a few of these terms by putting n is equal to 0, 1, 2, 3, 4, 5, 6. Find a few of the terms and identify what this sequence is. This is a sequence. Once you see what it is, you should be able to identify a pattern in the numbers that you get, and it should be a sequence that is very familiar with you. One of the things we would be doing later in the semester is we would be looking at, if I have a sequence written in a recurrence fashion, then how do I find a closed form solution to it? And this would be one of the examples we'll study for that. This is another interesting sequence uh, where the nth term is obtained as 1 plus 1 divided by n to the power n. What I want you to do, and for this I would ask you use something like Excel, some sort of a spreadsheet software, Google Slides, whatever. Sorry, not Google Slide, Google Sheets, uh, to write a formula that will help you compute these sequences as a pattern, so that you can put the value of n and you can compute the value of e of n very easily. What I want you to do is I want you to find numbers that are large values of n, and what you should see is that in that case the numbers start getting very close to each other. E100 would be very close to E101, E99, etc. This is a sequence that converges to the number e, which is what we use in the context of natural log, etc. Once again, we have reached the check before you go ahead slide. The key thing I want you to be able to do from here is compute elements in a sequence given a formula. So we had some formula earlier about ways to compute the nth term in the sequence. Given that, you should be able to figure out what it is. Also, I want you to look at the two examples of sequences that we had and see if you can recognize those sequences by computing a few members of that sequence.